2. This might be the 20th revision stream of the year. I don't know. But what I do know is we have a test tomorrow. And it is specifically on actually quite a bit of content that I've already covered. Mainly on synapses. And then content which I haven't covered yet, which is neuromuscular junctions. And basically muscle contraction, the sliding filament hypothesis. Now, to be completely honest with you, I am really tired. Today has not particularly been a good day, but we need to get this done. So unfortunately, we are just going to have to crack on with this and try and get it done as best we can. So the plan is, I'm going to go over inhibitory... I can't pronounce inhibitory synapses and excitatory synapses. I'll go over those because that's the easiest thing, the thing that I know the most about. Then from there, it should be fairly easy, I think, going over sliding filaments. So, first things first is the synapse, which I can never draw right. That's something like this, okay? We need to know the parts, and we need to be able to kind of label this properly. So, where's my pen? Here we go. Firstly, we have sodium ion channels. Okay, well, firstly, we're going to assume that this is an excitatory synapse. Another word for that is cholinergic. And we'll explain why in a second. So let's assume that these are sodium ion channels here. Okay. Then we have receptors. Then we have vesicles, and inside those vesicles is neurotransmitter. For example, in cholinergic synapses, it's acetylcholine. And then finally, we are going to have, obviously, the labels. This is the synaptic cleft. This is going to be the presynaptic. That's going to be the postsynaptic knob. So. Basically, the action potential is going to arrive. And when the action potential arrives, the first thing that is going to happen is it is going to cause, and that's what I forgot to draw, CO2 plus. It's going to cause CO2 plus ion channels to open. So obviously, because they've opened, CO2 plus ions are going to diffuse into the postsynaptic neuron. And that will probably give you a mark point in an exam. The second thing we now need to talk about is the fact that the arrival of calcium ions into the presynaptic neuron causes the vesicles containing neurotransmitter to fuse with the membrane. And when it does, it's going to release the neurotransmitter into the the synaptic cleft, where it will then diffuse to the postsynaptic cleft via, obviously, diffusion. Then from there, the neurotransmitter is going to bind to the receptors on the postsynaptic membrane. You have to specify that these are on the membrane. And you should obviously specify here fuses with membrane, diffusion, membrane, etc. Now, when the neurotransmitter binds with these receptors, it causes the ion channels that the receptors are on top of to open, which is obviously going to cause sodium ions to diffuse in, and obviously if it reaches the threshold potential, it's going to trigger a new action potential. So, that is, it's rather simple, and the only difference between excitatory, and I'm just going to call it non-excitatory because I cannot pronounce that word for the love of me. The only difference is these sodium ion channels are instead going to be, what is it? Is it chlorine or fluorine? It's chlorine, I think. It's going to be Cl minus ions, chloride ions. And this is in inhibitory synapses. So these are chloride ions. They're negatively charged. So what that means is when we have chloride ions diffusing in, it's going to create a negative potential, which obviously, if we look at our action potential graph, it obviously needs to reach the threshold potential in order to trigger. Oh my god. Right, okay. Because this is an example of positive feedback, which we have just covered. Positive feedback, in this example, is going to be where when a few Na plus ion channels are open, more will open in correlation to the scale of the stimuli. So I think this is a really simple concept. Honestly, obviously, just remember the word cholinergic, because then you'll know from that it's excitatory. If it's non-cholinergic, then it must be an inhibitory. I can't pronounce that fucking word. Inhibitory. I don't know. It inhibits. It inhibits the action potential. I'm not crazy. Right. Let me go and try and find a mark scheme. Because what I want to do now is I need to make sure that we're correct. I want to make sure I'm not missing any mark points for tomorrow. Oh, there are some mark points I forgot. One, and you will guarantee get a mark for this, so don't forget it. The arrival of sodium ions is going to cause depolarization. The arrival of chloride ions is going to cause hyperpolarization. Just two little keywords that you can always include. Remember, obviously, another keyword is the membrane. You have to say the receptors are located on the postsynaptic membrane. You cannot say that they're located on the neuron. You have to specify membrane. So I just want to check whether I've written anything in the revision document about this. Causing vesicles diffuse with the membrane. Diffuses through the cleft. Binds with the receptors. Diffuse into the neuron, depolarizing. This triggers it. Okay, so according to my mark scheme that I have written myself, I've got this all right. I just want to go into Physics Math Tutor and try and find a mark scheme that they've written, because usually there is 1 or 2 mark points. I don't know what it would be under. I'm guessing receptors, maybe? I don't actually know what it would be under. Just going to type in... Oh, I can't find a mark scheme. That's really odd, because usually they have them. Receptors, survival and response, nervous coordination, maybe? Surely that would be it. Oh, here. When a nerve impulse arrives at a synapse, it causes a release. That's question 5. Nerve impulse causes CO2 plus channel proteins to open. They enter by diffusion. Synaptic vesicles fuse. Okay. Yeah, that's right. Obviously, you could talk about the effect of drugs. That could be a question. Remember that if, for example, a drug might bind to, so for example, there are enzymes, and the enzyme's whole purpose is to get this neurotransmitter and recycle it. Basically converting acetylcholine into acetyl and choline. Now, the important thing is, if these enzymes are inhibited, then it means there is more acetylcholine, which means it's going to be, you know, more readily available to carry the impulse. Another thing to note here should be, and I've completely forgotten what I was going to say. Shit. Oh my god, I've completely forgotten what I was just about to say. Oh no, I forgot what I was gonna say. It's an exam question. You might. Oh, come on, I am this close to remembering. In an exam, one of the typical questions they ask, if it's not about drugs, it'll be about, I don't remember. Okay, well that's annoying. Should we quickly do temporal and spatial? This is very simple. Spatial summation would be, for example, with the rod and cone cells, well, specifically the rod cells, where multiple rod cells are connected to the same bipolar cell. So spatial, what we have here is we'll draw I'm just going to draw it like this. Spatial is going to be where you have multiple synapses releasing their neurotransmitter, which means that more neurotransmitter overall is going to reach the postsynaptic. And temporal is literally where there is just an increased frequency of neurotransmitter being sent over a short period of time. So spatial is where there are literally more in a space. Temporal is where there are more in time. So that's a very simple concept, but you could get asked about that. The advantages of both, the disadvantages. Final thing now is nervous coordination, specifically the sliding muscle hypothesis. So, I am going to attempt to recall this from memory, and we will literally just see how this goes. In fact, one second. Okay, cool. Okay, so we have, first of all, a motor neuron. This will take a bit of explaining. Do not worry. Because this is a gigantic process. Motor neuron, and then we have our muscle tissues. We have our T-tubules, which are basically, I think the way to describe these would be like indentations in the membrane. Extensions of the membrane. So T-tubules are extensions of the membrane. So when our neurotransmitter, acetylcholine, we know this already, when the action potential arrives, cough cough, it causes the vesicle to diffuse, and the neurotransmitter will diffuse through the T-tubules, where it will, I don't recall specifically where, but during this process, it causes the release of CO2 plus ions. Now, the specification of these is that they are released because there is the sarcoplasmic reticulum, which I'm going to draw like that because that's how the RER looks. This is the sarcoplasmic reticulum, and this is what stores the CO2 plus ions. Okay? And when the neurotransmitter reaches the sarcoplasm, it is going to cause the release of CO2 plus ions. Now, this is where we get into the overall sliding filament hypothesis. What we have is we have a layer of actin, so I'm going to draw it very small to begin, and a layer of myosin, like so. And we have different bands. For example, the Z band is the distance between filaments, which I forget the name of. Sarcoments, I think. The A band is going to be... Wow, I need to Google this. I always get this mixed up. I know what it is. I know what it is. I just don't know how to draw it. That's the only thing. I can't draw it. Sarcomere, yeah, I was right. So that's a sarcomere, which is just the distance between two Z bands. You have your thick filaments and your thin filaments, these. I should probably draw these more like on top of. In fact, I'm gonna try and draw this over here, just so. Okay, so we have our Z bands. We have our A band, which is both actin and myosin. We have our I and H zone. Okay, wow, I need to Google this. So the H zone is specifically where it's just that, and the I band is just the actin. Okay, so I hope that makes sense. Oh my, what? Oh, okay, hold on. I gotta read that later. That's crazy. So that is the sarcomere. And the reason this is important is because we need to be able to describe specifically myosin and actin and the role that that has. So that is myosin, the thick filament. This is actin, the thin filament. Crazy, okay. So, we could probably get on with this sliding filament part now. And then we should be good for this whole topic. So, what we have is, in summary, I'm trying to find a good pen to use here. We need a good pen. Okay. What we have in summary is this is going to be our actin. And we are going to say that this is an actin binding site for myosin. Because the thing is with myosin is it's like this very thick molecule, very thick thing, but it has on it two heads. It has heads, and what these heads do is they bind to that binding site on actin. So, that is very important to note. The binding site. So, what we are saying is, to begin, you have troponin and tropomyosin. Troponin and tropomyosin. Now, because of the influx of CO2 plus ions, troponin is going to undergo a conformational shift, basically in shape, changing the tertiary structure. Tropomyosin is going to be displaced. So, these were initially covering the binding sites, but now it's open, which allows our myosin to come along and bind with it. Now, this is where it's important to note the importance of ATP and ADP. To begin with, we have the head is going to be bound to ADP, and that allows it to bind it is going to change angles when bound, and that causes the actin to be pulled, and this causes the ADP to, I don't remember the word, like, displaced. You motherfucker, I just pulled my leg. Hold on. Oh, my legs. ADP is just released. ADP release. So from there, the head is going to ATP binds, and this causes it to detach from the filaments. And then finally, the hydrolysis of ATP into PI is going to lead to myosin being returned to its normal position. So, I want to check any mark schemes I can just to figure this out. But yeah, obviously active transport when talking about movement of ions. Myosin heads bind with actin binding sites, forming actor. Oh, it's actor-myosin cross-bridge. That is just a very tiny but very powerful word that you can always get a mark from. That's just something I thought I should know as well. The actor-myosin cross-bridge. What else is there here? Myosin changes shape, causing the head to move forwards. This movement results in the actin filament moving over. An ATP molecule binds to the myosin head, causing the head to detach from the actin. ATPase breaks down the ATP. This causes a change in the myosin head. Okay, so that should be fine to explain. Trying to find the past exam questions we did just so I can add some more, but I don't recall if we got any. Obviously, the importance of ATP itself is that it is adenine, a ribose, and then 1, 2, 3 inorganic phosphate. The whole purpose of ATP is that it is used in phosphorylation. It can easily be regenerated by a condensation reaction. Rapidly resynthesized. And it also does not contribute to it cannot move out of cells. So that is adenosine triphosphate. Tropomyosin covers the binding site. Myosin will attach to the exposed actin, changing shape, causing it to be moved along. It will then obviously unbind and rebind. Capillaries provide oxygen/glucose for respiration, and a high rate of it. Calcium ions diffuse from sarcoplasm, causing tropomyosin to become displaced, /troponin to undergo conformational shift. Exposes binding sites on actin. ADP on myosin head is released when myosin head binds to actin binding site and changes angle. Hydrolysis releases energy. Okay, I think we're good to stop there, honestly. I'm happy with that. I'm very happy with that. So that is everything for today. Hopefully that was helpful. That is a very nice overview of what I would argue is a very difficult topic. But